Hello, class. We're going to do chapter 2.3, Atomic Structure and Symbolism. The objectives are to write and interpret symbols that depict the atomic number, the mass number, and charge of an atom or ion, to define the atomic mass unit and average atomic mass, and calculate average atomic mass and isotopic abundance. The nucleus contains the majority of an atom's mass. Protons and neutrons are much heavier than electrons. Electrons occupy almost all of an atom's volume. The diameter of an atom, of course some atoms are bigger than others, but is about 10 to the minus 10 meters, so it's less than a nanometer, 10 to the minus 9th. The diameter of a nucleus is 100,000 times smaller, or 1/1000th, than 10 to the minus, the diameter of a nucleus is 10 to the minus 5 smaller than that of an atom, so around 10 to the minus 15th meters. They're always comparing atoms to football fields, so they're saying if the nucleus was the size of a blueberry, the size of the atom would be a football stadium. Atoms and subatomic particles are very small. An atom weighs less than 2 times 10 to the minus 23 grams. Of course, each atom weighs differently according to its atomic number, atomic mass. Electrons have a charge of less than 2 times 10 to the minus 19th coulombs. It's actually 1.6 times 10 to the minus 19th coulombs. Small units are needed. The atomic mass unit, and we will get into this more, it's a very small number, 1.66 times 10 to the minus 24th grams, and the mass of carbon-12 of a carbon-12 atom is exactly 12 atomic mass units. Originally, it had been defined in terms of the mass of a hydrogen atom, but in terms of standards, they found that carbon was much easier to work with, and it could be purified more easily to carbon-12. And just because everything was easier, they defined carbon-12 as 12 atomic mass units. And that's why hydrogen comes out to have an atomic mass unit greater than 1. The fundamental unit of charge, just as I said up there, is 1.602 times 10 to the minus 19th coulombs. The proton, you see, it has a mass greater than 1 atomic mass unit. It has a charge of +1, which means it's 1 electron charge, or 1.6 times 10 to the minus 19th coulombs. The neutron has a mass slightly greater than the proton, with a charge of 0, and the electron has a very, very tiny mass, about 1/2000th that of the proton, and the charge is a -1. The number of protons in the nucleus of an atom is its atomic number, or Z. We're going to talk about the periodic table in the future, but the periodic table was compiled based on the atomic weights, which can be gathered by ordinary wet laboratory experiments. The atomic number came out of X-ray analyses in the early 20th century, and was found to correspond to the number of protons in the nucleus of an atom. And the periodic table was subsequently ordered according to the atomic number. This is the defining trait of an element. Its value determines the identity of the atom. For example, any atom that contains 6 protons is the element carbon and has the atomic number of 6, regardless of how many neutrons or electrons it may have. A neutral atom must contain the same number of positive and negative charges. The number of protons equals the number of electrons. Therefore, the atomic number also indicates the number of electrons in a neutral atom. Of course, the number of protons and neutrons in an atom is called its mass number. The number of neutrons is therefore the difference between the mass number and the atomic number. The atomic number of Z is the number of protons. The mass number, A, is the number of protons plus the number of neutrons, and A minus Z equals the number of neutrons. When the number of protons and electrons are not equal, the atom is electrically charged and called an ion. Charge of an atom equals the number of protons minus the number of electrons. Atoms and molecules acquire charge by losing or gaining electrons. An atom that gains one more electron will exhibit a negative charge and is called an anion. It helps to focus on the N of anion to think of it being negative. Example, a neutral oxygen atom, its atomic number is 8, has 8 electrons, and if it gains 2 electrons, it will become an anion with a 2 minus charge. 8 minus 10 equals negative 2. An atom that loses one or more electrons will exhibit a positive charge and is called an cation. Example. Oh, by the way, think of the T in cation as a plus sign, and that's a mnemonic for understanding that a cation is a positive charge. Example, a neutral sodium atom, Z equals 11, has 11 electrons. If this atom loses one electron, it will become a cation with a 1 plus charge. 11 minus 10 is plus 1. I don't know why they threw this in here, except as an example of a compound that we come across often that contains iodine, which is another an element that we need to be aware of. A chemical symbol is an abbreviation that we use to indicate an element or an atom of an element. For example, the symbol for mercury is Hg. Elements always have a capital letter, and many of them have a lowercase letter. And that's the general structure of them. They have the uppercase and lowercase letter, and some of the early ones only have an uppercase letter, like hydrogen and oxygen and fluorine. Some symbols are derived from the common name of the element, and others are abbreviation of the name in another language. Most symbols have 1 or 2 letters, but 3-letter symbols have been used to describe some elements that have atomic numbers greater than 112. Only the first letter of a chemical symbol is capitalized. The symbol Hg represents the element mercury, regardless of the amount. It could represent 1 atom of mercury or a large amount of mercury. By the way, it can also be part of the representation of a mercury ion as well. Some common elements and their symbols: aluminum, bromine, calcium, carbon, chlorine, chromium, cobalt. Copper is Cu for cuprum. Fluorine, gold is Au for aurum. Helium, hydrogen, iodine. Iron is Fe for ferrum. Lead is Pb for plumbum. Magnesium, mercury, Hg for hydrargyrum. Nitrogen, oxygen, potassium, K from kalium. Silicon, silver, Ag from argentum. We also get the name for the country Argentina from that. Sodium from natrium. Sulfur, tin from stannum. They call it stannus in stano in Spanish. And zinc. The symbols for a specific isotope of any element is written by placing the mass number as a superscript to the left of the element symbol. Okay, so isotopes vary by the mass, and so the symbol is the symbol of the element, but with a mass number as a superscript to the left. The atomic number is sometimes written as a subscript to the left of the element. But here's the thing, is the atomic number defines what the atomic symbol is. They don't give you the numbers on this page, but it's actually redundant. That is, the symbol and the atomic number are always intricately linked. C is always has the atomic number 6, H always has 1, oxygen always has 8. For example, magnesium exists as a mixture of 3 isotopes, 24 Mg, 25 Mg, and 26 Mg. All isotopes have 12 protons in this example, but the number of neutrons are different. And so we have the mass. Here's a isotope, and in this case it's an ion. So we have the atomic symbol He and the atomic number, and those will always be linked. Anytime you see He, it would have the atomic number, which is sometimes omitted here as 2. In this particular case, we're talking about the isotope that has the mass, atomic mass of 4, which is the most common kind of helium. Science fiction is talking about recently about collecting hydrogen-3 off the moon, where it's collected from the solar wind. And it can be charged, that is, it can have no electrons. In this case, believe it or not, this is also called an alpha particle, a kind of radiation, just the bare nucleus of a stable helium-4 atom. And here is a particular charged isotope of magnesium. Magnesium always has 12 protons, a mass, in this case, one of the more common isotopes is 24, and it commonly loses 2 electrons in the formation of compounds, and it is oftentimes found in compounds as magnesium 2+. to be honest, is not found in as any other ion normally in chemistry. But there are some metal ions that can adopt multiple charged states in different ions. The symbol for an atom indicates the element via its usual two-letter symbol. The mass number as a left superscript, the atomic number as a left subscript, which is sometimes omitted because it is redundant to the symbol, and the charge as a right superscript. Hydrogen exists as a mixture of three isotopes. This is the only element I know of in which they've actually given a different elemental name to the different isotopes, mainly because these isotopes are more different with hydrogen than they are with other elements, because it changes the mass substantially. To go from a mass of 1 to a mass of 2 is doubling the mass, and 3 is tripling the mass. So they call ordinary hydrogen, the most abundant form, they call protium. Basically, it's an element, an atom made from a proton and an electron, and therefore it's called protium. When there's a neutron involved, it has twice the mass and is called deuterium. And with 2 neutrons in the nucleus, it is called tritium. This configuration is not stable. It will emit radiation in the form of beta rays, that is, emit high energy electrons and turn to helium-3. So they all have the same atomic number. They all have the same number of protons, which is the definition of the atomic number. They have different number of neutrons, which defines the mass. And as you see, the natural abundance is 999, and that's almost 9. And this is 1 part, this is 1% of 1%. So it's 1/10,000th. Every atom in 10,000 is a deuterium. When we go to fusion power, we'll be collecting this out of the ocean. And believe it or not, we're not going to need very much for substantial power. Atomic mass. Each proton and each neutron has a mass of about 1 AMU. Each electron weighs far less, about 1/2000th of an AMU. Therefore, the atomic mass of a single atom in AMU is approximately equal to its mass number. However, most elements exist naturally as a mixture of 2 or more isotopes. The periodic table lists the weighted average mass of all the isotopes present in a naturally occurring sample of that element. And this is just how that average is going to be completed. We'll do more of this in the problems. Mass spectrometry. It's the occurrence and natural abundance of isotopes. Let me start over. The occurrence and natural abundances of isotopes can be experimentally determined using an instrument called a mass spectrometer. The sample is vaporized and exposed to a high-energy electron beam that causes the sample's atoms or molecules to become electrically charged, typically by losing 1 or more electrons. These cations are then separated by their mass and charge. So this shows a mass spectrometer. There's a magnet, there's a sample chamber where the sample is introduced as a gas. A heater vaporizes the sample, it forms a gas here, and it is ionized. In this case, it says with an electron beam source. It could be ionized with X-rays also. And the ions are accelerated using charged plates. In this case, it's forming a slit. And that slit is separated by bending it in a magnet. And because different ions have different charges, actually charge to mass ratios, they bend differently in the magnetic field. And they appear in this charge to mass ratio diagram where the different abundances in the sample are seen. By the way, there's so much chemistry involved in the beam itself. In this case, like if you have a pure element like carbon or nickel, it will form clusters. And this is how C60 was discovered, or Buckminster fullerene. It was discovered that when you vaporized carbon here and ran it through a mass spectrometer, that you had a mass to charge ratio peak consistent with 60 carbon atoms. And a man named Smalley, Richard Smalley, reasoned that a soccer ball structure has 60 nodes on it and would be consistent with that peak. And that's how we know, that began Buckminster fullerene. Okay, we've reached the end of that section, and we shall continue later. Thank you for listening. Bye.